Hey guys, it's Mr. Sheeline here for the Unit 6.2 notes covering universal law of gravitation, or law of universal gravitation. So, something to watch out for is that I usually get these not so much mixed up, because that sounds like, it makes it seem like it's incorrect to say either way. Just understand that I'll call it the universal law of gravitation, I'll call it the law of universal gravitation. Arguably, it's better to be called the law of universal gravitation, but we're focusing here on how it is that gravity affects all things within all time across the entire universe. So, getting straight to it. So, first thing we have to understand, gravity is everywhere. Gravity is present wherever there is matter, okay? So thus, all material things are exerting some kind of force on all other material things at some time, at some capacity, and by some time I mean all the time. Okay, so some little speck of dust 100 million light years away from here is having an effect on the gravity you're feeling right now, okay? You, more or less, the same size as that speck of dust 100 million light years away, you, in reference to, say, like the Earth, the Sun, and the Moon, are also, even though it's super crazy small, exerting a gravitational force on something 1 billion light years away, okay? Doesn't matter in the size, doesn't matter how far you are away from something, gravity is affecting everything and anything in the known universe at some capacity, at some level. And we're able to find that by using this equation right here. This is our law of universal gravitation formula. Force due to gravity is equal to big G, which big G we'll get into in just a second, times the mass of our first object times the mass of our second object divided by the radius squared between the centers of our two objects. Okay, so it looks like this. We have our mass of object 1, mass of object 2, and what we're talking about is the attraction force between both of them. Okay, there's a force that's pulling these guys together, and this force is this gravitational force. Okay, and the way that we're able to measure it is by taking the radius, so taking the distance from the center point of this mass and then measuring to the center point of this mass, and just measuring that out. Okay, so that's the radius, the masses of how much mass each one has, and we're going to multiply all this by big G. Now big G, what this is that it's the universal gravitational constant. So gravity is affecting, like I said, all things. It's a long distance, it's called a long distance force. It's a field force that acts on all things regardless of distance at all times. And more or less we can, this is something that Newton devised, was that there must be a value that indicates how gravity affects all things regardless of space, time, distance. And that constant is the 6.67 times 10 to the negative 11th Newton meters squared, and that squared is only on the meters, divided by kilograms squared. Okay, so that's big G, the universal constant. Okay, and we again use this formula to talk about and to describe what attraction forces are between two objects. Okay, so we're going to be using that here in our notes not too much longer. Now, here is something that is a little heavy on the calculus side that I don't really want to get into a whole lot, but I do want to still talk about it just for a half second here. So it's what we call the inverse square law, or the inverse square principle. So what the inverse square principle is, on its face, super duper basic, is that it talks about how there is a relationship between the distance, between the inverse distance something has and the force that is exerted between them. So what you'll notice here in this picture is that each time that we increase, each time that we double the distance, okay, more or less double the distance, or we increase it by itself. So if we start with D1, double it, well then D1 plus D2 gives us D3, every time that you increase the radius by its original amount, what you'll notice is that the force exerted on an object more or less decreases. Okay, that the more that you, and and by radius I mean distance. We're not exactly talking about, because it does depend upon the mass of an object, obviously. But if you were to take an object and you were to continually space it out the same amount each time, what you would notice is that when you space it out, each time you space it out by its original radius, the original distance, you're chopping that force literally in half every single time. Okay? And so again, it's just to talk about how the force is proportionate to the distance from between these two masses. And that's all I really want to talk about as far as that's concerned, because again, that gets into some pretty wicked calculus pretty quick. And I really don't want to do that here. We're going to keep it nice and simple, keep it much more, trigonometry, algebra based than anything. Some considerations. So gravity acts between two objects, obviously. That's represented in the formula. That is something that we have been seeing. Now, these equal forces, these are equal forces though, and they're acting in opposite directions. So don't think, if you've got mass of our first object here, the mass of our second object here, don't think because mass of this object is bigger that all of a sudden, for whatever reason, that it's going to have a larger force on this guy. Okay, now there's some truth to that, but what we're calculating here is what is the equal shared attractive force between them due to both of their masses. Okay, it takes into effect the different masses, and we're just worried about what's the equal but opposite reaction forces of the gravity here. Masses must be large to notice a g-force. So as much as you'd like to think that, oh, I'm affecting that little particle of dust, the 100 million light years away, yeah, that's cool and all, but it's such a small calculation that it is almost not even worth calculating. You really don't feel a g unless you have a particular mass, unless you are of a super duper big size in relationship to whatever you're talking about, whatever the relationship is to something else. So that's why, like, yes, you do have an effect on the speck, the 100 million light years away, but what is going to have a bigger impact, you or the Earth? And hopefully we should understand it's the Earth, because the Earth has roughly it roughly has we'll just say the Earth is so large that you are insignificant. Your mass is insignificant compared to the Earth's. Okay, but you, yes, do have an effect on something somewhere, but Earth overshadows you by a long shot. So that's why it says here, Earth doesn't notice an individual pull on it, but we notice its pull on us. Okay, and it's one reason why we can't fly. It's because Earth is like, yo, I'm way too big here, man. You want to jump up and fly like Superman? That's cool, but I'm such a large force. Space and time is bent towards me. A whole lot more is bending towards you. So you're going to come towards me, not the other way around. Okay? Also, that's neglecting, too, the centripetal force that's also pulling us towards the center of the Earth as well. So that plays a part as well, because the Earth is rotating. It is moving at a tangential speed in relationship to the sun. So you have both this mass gravitational pull, and you also do have a centripetal force that is also carrying you towards the center of the Earth. Other considerations we should have. The more further apart, the smaller the force of gravity. And that should be fairly obvious. Okay? If gravity is reliant upon how close one another two objects are and their masses, if you pull them away, it should make sense that, oh, well, yeah, your gravity is going to decrease. Sorry for the bell. But we should also understand that it's never zero. In space, we do, if we were just to float around, we do experience very little gravity. But it is still gravity that is affecting us. Now, if you were able to get an object to be perfectly still, Would there be a gravitational force that will eventually pull it towards another object? Depends upon how large that other object is and how far away you are from it. But let's say that you are, let's say the closest thing that is, the closest object to you is, I don't know, we'll say if it's like 100 trillion light years away, and the thing that is closest to you is the size of the sun in our solar system, will it have a gravitational effect on you? Yes, it will have a gravitational effect on you. Will it be so much that it'll draw you towards it? Not really. It'll be so small that for the most part, more or less just the general velocity that the universe is already expanding will be greater than the gravitational force on you. And that'll take precedent over that. Like you'll actually slowly move farther away from whatever the closest object is to you than you would move towards it due to its gravity. But there still is some sort of gravity affecting you at some capacity, and that's why it's called a microgravity. So to answer the question that I posed is that no, like the object would pretty much stay perfectly still if you were able to get it perfectly still. And it would remain that way forever until something came up and poked it. Okay, or got close enough to it, a large enough mass got close enough to it to where then the gravity does draw it in. So what we can do with the power of big G is figure out what the gravitational acceleration is of a planet. As long as we know the gravitational, or as long as we know the radius between them, as long as we know the masses of both planets. And so we're going to be working a little bit with excuse me, this table here. There's also going to be another table we're going to use in a couple of practice problems. So this is what it looks like. So you've got the particular planet, which I understand Pluto's on here, and we all know that Pluto is no longer categorized as a planet. It's still a celestial body, but it has been labeled as, I believe, it's a white dwarf. So back in the day, it used to be a star. Now it's basically a dead star. But it's not considered a planet because of that. So yes, I know Pluto's on here. I understand that. We're going to keep them on here just because it is a relatively large mass floating around our solar system that does have a mass that's affected by all the other masses by the sun within our solar system. But here's what I really want you to notice. I want you to notice, like, look at the sig figs that are used here. Look at the radius, specifically the radius from the center, the most center point of these objects to the most outer part of the objects to the surface. Notice how big these numbers are, but look how small their sig figs are, especially for the mass. Look how massive these things are, okay? And notice how small these sig figs are. So just so you're aware, when we do the calculations with these, we have to be a little extra super careful with the amount of sig figs we're using during our calculations, because and I know I've never really had you guys keep sig figs. It's just something to keep an eye out for. If you were to have a worksheet that instead of using Mercury's mass of 3.2 times 10 to the 23rd, and instead used like 3.19 times 10 to the 23rd, and if you didn't keep 3 sig figs, that could really, really mess up your answer by a magnitude of, say, like 10,000, okay? So just be careful. Be careful. Use your best intuitive knowledge in order to say, like, hey, that number must be too small. This number must be too big. Maybe I should double check my answer here. Maybe I should get a hold of Mr. Sheeline to double check my answer. Okay. So notice that. Other thing I now want you to notice is this. Let's just take a peek at who has the largest G-force. And what we'll see here is that it's Jupiter that has the largest G-force. Okay. Well, let's see what the radius is. Okay, it's about, sorry for the bell. It's about 7-ish, 6.98 times 10 to the 7th meters. Its mass is 1.901 times 10 to the 27th kilograms. Okay, that's cool. Well, let's take a look at what would have the smallest G. Okay, which is Pluto. Pluto has a radius of 1.15 times 10 to the 6th power, so not very big compared to Jupiter, not big at all. And then it has a mass of 1.2 times 10 to the 22nd kilograms, so significantly, by a whole order of five units in our exponents. Okay, that's 5 whole zero placements. Okay, that's like going from 1 to 1, 2, 3, 4. That's like going from 1 to 100,000. Okay. Let's see, right? Yeah, 1, 2, 3, 4, 5. Yeah, it's like going from 1 to 100,000. Like, that's how big of a difference the mass is between Jupiter and Pluto is. And what we notice here is that this large jump, okay, has a drastic decrease, or it has a drastic effect on the particular G-force on the planet, okay? Because it has a smaller radius, because it has a smaller mass, it has thus a very, very, relatively speaking, weak gravitational force, okay? And so that's something we'll have to keep an eye out for. So we have these check your understandings. Make sure you complete the check your understandings. I'm going to skip right past them so I can continue with the notes. I'll have a separate video with those check your understandings, so make sure you watch that after you finish all of this. So objects in circular orbit. So we were just talking about how we can calculate the gravitational force of a planet using the attractive force between two places, two objects. And so we're going to continue working with that here, only this time it's going to be with satellites. And so remember, satellites are not always just the things that go beep, beep, boop, and you know, blink, and you know, the things you get confused with shooting stars when you're trying to look for shooting stars at night. And some of those are planes, arguably, but some of them are satellites. Satellites are just anything that pretty much maintain a circular path around another celestial body, in this case Earth. So there's all kinds of debris, there's all kinds of rocks that are out within a particular distance from the Earth that are technically satellites. They just happen to they move around the Earth. And that makes a big distinction, because either you're a satellite or then you're just, more or less, you become a projectile slingshotted away from the Earth, or you start crashing towards Earth's surface to where you become, for a rock's case, you become an asteroid, or not an asteroid, sorry, you become an asteroid, and then that becomes later on a meteorite when it hits the surface. But anyway, it's an object in space. Objects in space orbit larger masses due to the force of gravity between them. So let's just get to what a satellite is, and it's just this. Again, due to the large mass of Earth, we have satellites that move around the Earth at a particular rate due to its distance and the mass of a satellite. Okay. And so why is it that they just don't get pulled down, though? Well, it's because it's at, you know, the satellites were launched at a particular speed, at a particular angle, with a particular mass, at a particular time, to where it could be a particular distance from the center of the Earth, so that it could continue to move at a particular tangential velocity around the Earth in order to more or less stay within like free fall. So the satellites want to move in this forward direction, but because there's the pull of gravity, it's kind of locked. It can be locked in this spot where it continually falls towards the Earth. Okay? More or less, that's what's happening with the ISS. The ISS is moving at such a rate around the Earth, and it is such a mass, particular size of mass from the center of the Earth, that it is both falling and also moving at a rate around the Earth that allows it to stay up in space. If you were to somehow alter it, if you were to, say, counteract the pull of gravity by, say, pushing up like this, like if you were to shoot air down and then allow it to move opposite to the gravity, you would get closer to just the ISS being slingshotted away from the Earth. If you did the opposite, where you pushed a little bit this way, then eventually the ISS would come down, crashing and burning, literally crashing and burning to the Earth. Okay, so it's locked in this nice little sweet spot to where it's just chilling, hanging out, moving at a constant rate around the Earth, to where it's basically in free fall. Okay. And we can calculate how quickly that's moving using basically stuff that we've already been using before. Okay, so we're going to take the gravitational equation, and we're going to mix it with the centripetal force equation in order to basically say this. If we want tangential velocity, we're going to take big G divided by the bigger mass, all square rooted, and divided by the distance between those two objects. Okay. We can also use the equation here to know how quickly or how slowly something is moving around the Earth. So we can use, again, period, frequency equations we've used before. What's the mass of our large object? How far apart are they? What's the force between them, as long as we know the force? And if we know the force, then we can solve for the period, or we can solve for the frequency. And here's to check your understanding for number 3. Make sure you complete that. And so this has some implications. Okay. So this is a GIF in the actual slide, so I'd recommend you look at the slides to see this GIF. But geosynchronous orbits are something else that we're going to take a look at. So I mentioned a sweet spot that the satellites are typically held at. Well, there's an even better sweet spot where if we want geosynchronous satellites, we have to launch them out to a particular distance away from the Earth in order to be locked in and be looking at one spot on the Earth at all times. So this means that the object stays in the same place relative to the Earth and will always point in the same location. Okay, and this is most useful for like communication satellites. This is most useful for, say, was it HughesNet? The satellite internet stuff. This is like cell phone, some cell phone satellites. This is like DirecTV satellites, dish satellites, that sort of thing. If dish is still a thing, I haven't seen a dish commercial in so long, and a DirecTV commercial in so long. God bless. They're getting phased out because of Netflix and all that. But anyway, I digress. And as an example here with this GIF, it's basically like you have the satellite that's right here. We can, well, and this is something we're going to solve for, is to figure out how far away it is, using how quickly it's moving, and what its period is, which, I mean, shoot, if it's geosynchronous, so meaning it moves, if it has the same period as the Earth does, well, shoot, that's already given to us. But this will be different. This will have to be given in order to find how far away it is, what the radius is. And then the rest here, I'll just quickly go through because this is really something we've already talked about in the last section, but just something I didn't include in the notes. So space travel, because we have to understand that gravity does play a huge part in space travel. Arguably, it's the most difficult thing that scientists have to take account for, because large objects have mass, obviously, and it's a lot of mass, and all of that mass has a gravitational pull, and we have to know how to, swerve around it, how to use it to our advantage. We can't just swoop in and swoop out right now into different atmospheres. You have to have a precise calculation of a particular area with particular pressures, with particular winds, with particular heights, at particular times, there's so many different variables that go into landing spacecraft on different planets. That's why it was such a huge thing just a couple weeks ago. As of right now, as of March as of March 15th, 2021, it was just like a month ago that they landed the rover they just landed a little rover on top of a asteroid. And that was such a big deal. It really wasn't an asteroid. I think it was technically a comet. I'll have to double check on it. But anyway, it was a large rocky mass that was floating around the Earth, and they landed a spacecraft on it, and that was such a big deal because there's so many different variables that go into this, into landing that object that deal with gravity. And anyway, so another part that sucks about, specifically interplanetary travel is the fact that we're creatures that are used to gravity. Not are we used to gravity, we are built in order to adjust to gravity. And when we don't have gravity in order to put stress on our body, healthy stress on our body, these things happen. Muscle atrophy, so we lose muscle mass. Loss of bone calcium. Bone density decreases. Okay? Why do your bones have to be dense if there's no gravity to oppose? Like, you have to understand your skeleton is made to oppose gravity. Your skeleton was specifically made in order for you to walk around, to run, to jump, and to do anything that you wanted to do, roughly speaking, and not basically crumble to the ground under the stress of gravity. And so when you take gravity out of the equation, bones are then like, your body's like, yo, there's really no stress on this dude, so, I think we can relax on making bones and repairing and replacing the calcium and all the cells within the bone and within your bones. So in that scene in WALL-E, when everyone on the giant cruise ship lands on Earth and then just like walks outside, no. They would have been crushed. Their knees would have like exploded. Their feet would have just, all their bones in their legs would have crumbled. And let alone that, probably would have happened on the spaceship when the captain, they basically mutiny and they like jump out of their chairs. Like, that it would have happened probably then, if anything, because their bodies weren't used to the stress. Their bones were not used to the stress and capable of handling that stress. Another thing is organ swelling, which makes sense because, again, when you have gravity helping you out, your heart is used to a particular set of pressures, a particular set of forces on it. Your heart works at a particular rate. And so when you take away forces, your heart has to work a little bit harder in order to increase and maintain, I should say, maintain the pressure throughout your body in order to stay alive. So you have organ swelling, like your heart swells, your kidneys swell, in order to just to get blood out throughout your entire body the same way it would on Earth. And then just the last stuff is, here's an image of what it looks like. One of an old little basically bicycle treadmill. It's on the ISS. It's one of the exercise equipments used on the ISS. They have a lot of resistance bands. There's a lot of like actual treadmills where you can adjust the amount of pounds of force that's being dragged on you. So stuff like that. And this is where it comes into long-term solutions. But what do? Well, we practiced what we do about this just last week, or at least in reference to right now we did. When we made our own spaceships, that's what we did there. We said, well, if we wanted to maybe not have so many issues with bone density problems, with kidney issues, with heart issues, with muscle atrophy issues, that we create a rotating spaceship that more or less replicates the gravity, that creates artificial gravity to allow people to more or less live somewhat normal lives while they're traveling through space. And then there's a last check your understanding. So again, make sure that you complete all the check your understandings, that all of those answers are going to be in a separate video. This is just me walking through the notes. If you still have any questions for me, guys, make sure you ask me anything later on. If not, I'll see you in the next one.